So I'm Alex Janik,
And I'm Samuel Roofer.
and we're obviously from G period, and this is our Beers Law lab. So,
Introduction. So the purpose of this experiment was to prove Beer's law in an experiment, and Beer's law states that the absorbance of light when shown through a solution is directly proportional to molarity. And basically as molarity increases, absorbance increases the same amount proportionally. And our hypothesis for this lab was that as molarity decreases linearly, so will the absorbance of the most absorbed wavelengths, and we're using that for accuracy purposes. All wavelengths should reduce by the same percentage, but just for accuracy, we're using the most absorbed. And also, using this information, we will be able to calculate the molarity of an unknown solution if we can figure out its absorbance. So, the first thing we did was we prepared 100 milliliters of a 0.100 molar cobalt chloride solution. We used math and molar mass ratios to figure out the proper amount to use. And then we used a cuvette of that solution. We analyzed that in the Spec 20 to find the wavelength of highest absorbance. And we added that point to a graph. Then we created 4 other solutions using the original 0.00 molar cobalt chloride solutions, and the molarity of these solutions were 0.020, 0.040, 0.060, and 0.080 molar, and we added those absorbances to the graph as well. And we did 3 trials.
so these are the 3 trials we did. Obviously, this trial is slightly off. You can see that this point isn't quite on the line. This trial is a lot better, and this trial is near perfect. And the way this is explained mathematically is the correlation value here, it's 0.97. That's still very high. The highest it can be is 1. Here it's 0.9978. That's very, very high. And 0.9999. That's literally the highest we could get it, because getting 1 is simply unrealistic, especially in a high school setting. So we're going to use this one for our data just simply because it's the nicest and the best, and we get the best results from it. So this is the slope and the y-intercept that we'll use to calculate the unknown solution. So the unknown solution absorbance at 514 nanometers is 0.216. Now 514 nanometers is the highest absorbance that we had of all the wavelengths for the 0.1 molar solution, which is why we used it. Now, so according to the third trial, the molarity would be 0.0432 based on this equation of, again, the y-intercept and the slope. So these are the class results that we got online. The class results were updated multiple times, so we're not quite sure which update we used in our math, but they're all fairly similar and should yield similar results, if maybe off by a number or 2. So first of all, we had to get the outliers out. The outliers were 0.1 and 0.06. Outliers are determined by the 3 sigma rule. If something is more than 3 standard deviations away from the mean, either too high or too low, then we take them out because they're probably going to mess up our math. So the mean of our class data was 0.045, and the standard deviation is 0.00391, which is very, very accurate. I'm very impressed with what the classes were able to do, and this just goes to show that how well they can do this. So this is the class graph. For some reason, this is showing us sigma of more than -3. For some reason, I'm not quite sure why. All I do know is that I wasn't going to Photoshop it because real scientists don't fudge their results, but just do know that this wasn't supposed to be here. This graph shows pretty much the sigmas of what the people got, and normally it'd go from like about here, kind of go down like this, and come down here. And this class is very different because this big section right here where the standard deviations are a lot less than what is expected, which is very good because, again, it shows the precision that everybody got with this lab. That's quite amazing.
Okay, so overall, like you said, our data was very precise. It wasn't very many standard deviations away. Our value was approximately half a standard deviation away from the mean, which is once again very, very accurate. More accurate than most of the people in our group. And also, our third trial helps to show how good Beer's law is in practice, because the correlation is 0.9999, which is very, very high. And that really helps show that Beer's law works, and it works to a high degree of accuracy. So In general, errors we could have had concentrations being off at the beginning or after we made the new ones. If we measured wrong, that would have changed our results. If the cuvettes were dirty, they might have absorbed more than they should have, which would have changed our results as well. General lack of time, that's generally an issue with most of the labs that we do in high school. But in this one, we had a lot of time left, so it probably wasn't a huge factor. And also improper mixing. If you didn't mix the solution right, parts of it might be higher molarity than others, and you might have not shown light through a solution of the molarity that you thought it was. And also, of course, you've got issues with the machine, but that's not really likely because a lot of the people were using Spec 20s. Actually, all of us were using Spec 20s. And if there had been issues, then we probably would have known because everyone would have them.
So, one interesting thing to note is that if the starting concentration was off, the graph would still look just fine because we're only taking parts of that solution. So, for instance, if the starting concentration was 0.15 instead of 0.1, all the other concentrations would be 50% higher than normal, but you'd still get a nice linear graph that could have an R value of 0.9999 or something crazy like that. But that would mean that their ending concentration of their unknown would be too high or too low depending on what their starting concentration was. So if their starting concentration was 0.15, then their unknown concentration would be 50% more than it is expected. Now this probably isn't a big issue, but for the people who had seriously crazy results, like especially the people that had the 0.1 molar, this could have been a major risk.
Yeah, if they made a math error and added way too much cobalt chloride, that would be an easy way to figure out where they went wrong.
So in conclusion, the data obviously supports Beer's law, and we know that because it's a law, but still it was quite nice to just be able to see it in real life and not just in the math or not just in the theory, and actually have it proven to yourself.
And good, it's so nice. So possible future experiments that we could do is basically the same thing but with more accurate measurements, maybe more data points, get a lot more trials in, and average them all out and get a nicer line, and figure out if that still follows Beer's law, which it should, but it would just be nice to show that even with more accurate techniques and equipment, that Beer's law will still be true.
Even so, this experiment would be fairly useless because we already know Beer's law is true, and there'd be no point to it besides just proving it.